to have here Christoph Anger from NVIDIA, who's going to give a keynote on NVIDIA's new exciting tech on doing data science on GPUs.
Thank you very much, and welcome everybody to the second day of FOSDEM. I hope you're enjoying it. I have to be honest, I had issues finding like all the interesting talks yesterday because there's so many, which is a good sign, obviously. So today we'll talk a little bit about RAPIDS, which is an initiative by NVIDIA, so I work for NVIDIA, an open source initiative for doing data science. As you probably are aware, NVIDIA is doing sort of neural network-based machine learning for quite a while now. With RAPIDS, we are also now looking into more traditional machine learning algorithms, so they're more in our focus now, and also sort of everything that goes around, not only the machine learning itself, but sort of the pre-processing, the post-processing steps. I hope to give you sort of an idea of what RAPIDS is, how you can contribute. It's open source, and in the end, we will have a couple of minutes for questions, I've been told. So if you have questions or anything, you can come to me either after the talk and we do it offline, or you can ask, obviously. So why is this interesting? As I said, NVIDIA is investing a lot of time in machine learning and artificial intelligence. The reason being that it's been sort of shown, at least by example. I mean, there's no proof obviously, but by example, that AI is transforming industries sort of across the board, right? So it's there are really products coming out that are actually doing things that have been unthinkable a couple of years ago. If you take healthcare alone, doing prediction and analyzing X-rays and MRI scans, detecting cancer early, which has been, if possible, then only with a lot of effort before, so as in human people looking at all the MRI scans. Now sort of machines take over a bulk of the scanning, and then the doctor is in the loop, of course, for the final diagnosis. In normal industries, defect detection, just material science, all those things is sort of disrupting a lot of the industries for making lighter weight cars, for example, lighter weight airplanes, finding new composites for fuels that burn better, and so on. I don't have to go through all of them. You can, I hope, imagine what the other ones would be, but of course consumer people, automotive, self-driving cars is a very popular or very heavily researched area where now car manufacturers are actually coming out with the first announcements for cars that are not fully self-driving yet, but have self-driving or close to self-driving capabilities. And then for RAPIDS, probably more interesting is more on the right side, so retail, financial industries, ad tech, and so on. Those are all industries that used machine learning already for quite a while. And they tend to use the more traditional machine learning approaches, right? So clustering, DB scan, things like that, or just linear regression. Those types of algorithms, they are not really necessarily jumping on neural networks yet, and that's fine. But with RAPIDS, we hope sort of to help those industries in addition. Now the thing is that data science, what makes it interesting is that data science is obviously not a linear process. I'm not sure who does the actual data science professionally or as a hobbyist in this room, but you probably know that it's not, it's not that you sit down, you write a code, you press play. I mean, that doesn't work with code anyway, but for data science, you have like this big loop that you're going through all the time, right? So you have data, you sort of have to prepare it. Then you try it out, your network and machine learning approach. Then you have to tune the hyperparameters, and then you try it again, and then maybe you prepare your data a little differently, or you get more data in, or you try it without the one piece of data because you have the feeling maybe that's disrupting your prediction, and so on. So you have, it's not like linear, it's like a lot of going in a circle. And now the thing is, if you look at those green boxes, which is data preparation, model training, and visualization, those three so the training of the model and maybe later the inference of or the predicting of outcomes is, of course, a big piece in this circle, but it's not everything, right? So it means if you reduce the size of this model training box, that's helpful, but it doesn't get you all the way, because the data preparation can be, as we'll see in a second, very significant. So how, if you became a data scientist and you've done it for a while, I'm not sure how many went through this experience, and if you have a different experience, feel free to speak up. But from my experience, it's, you became a data scientist because you want to work with data, you want to discover new things, right? But in reality, it looks like a day of your life. So you start at 9, let's say. Overnight, you sort of ran your latest prediction from yesterday, or you download new data sets or whatever you're doing. And then you start out with like doing a little bit of analysis, what happened overnight sort of, but then those green parts are the ones where you do ETL, it's called, so extract, transform, load. So that means you do maybe the training, maybe do the preparation of the data, you have to join it with other data and so on. And so starting at 9:45, you first can go to your first 3 or 4 coffees while you're sort of waiting for the one round to go. And then maybe after 12 you realize, oh dang it, I forgot those 5 new features, the idea I had last night, and I forgot to change it in this one file, right? And then you sort of have to start from the beginning and so on. So it can be a very frustrating process, right? Because it's slow. And obviously data scientists are very valued resources, they're highly sought after. So it does make sense, I think, to give them the tools they need and they deserve and require. That gets even more and more important, and you probably see when you work in data science, what this sort of uptake is and how many companies that may not even have thought that they are doing data science are suddenly looking for data scientists. Most likely they all did data science before, but not in that scale. And one of the reasons is that on the right side, that just the amount of data that we collect is continuing to grow, depending on who you believe, potentially exponentially, but at least it's so massive that you usually cannot just sift through all the data. Now, my assumption is that most of this data that is produced, that includes, I can't really read that, but it says like voice over IP and social media and web and so on. So a lot of the data that is produced in social media is maybe not the most, valuable that you need to necessarily analyze. But the problem is there is valuable data in there. So that means you still have to go through all the data and to find the valuable data. So even if the signal-to-noise ratio is going up like crazy, that still doesn't make your data science job easier, because you still have to find the valuable data, right, in the noise, sort of. And then at the same time, of course, the famous Moore's law is sort of at least slowing down, if not, depending on who you believe, came to an end by now. So that means this automatic, it just gets faster by waiting another year for the next computer. That's not working anymore. So if you look and you sort of see this effect in a traditional data science basement, I'm not sure, like you may have seen those, right? Sometimes you can probably to your university ones. You see racks after racks after racks of server computers, and it's loud and noisy and so on. And this would be essentially the equivalent that can handle a data set that's from Fannie Mae, the mortgage data set. And those would be 300 servers worth like $3 million, runs at 180 kilowatts. And you can replace like this whole machinery with essentially this, a DJX 2 box. A DJX is sort of an NVIDIA appliance. You can buy similar appliances from other vendors that also use NVIDIA GPUs in them, but that is sort of our model platform, right? And this whole thing sort of replaces, this whole wall of computers essentially in speed, and it's even significantly fast. If you look down here, so it's not only speeding up, but even you cannot really get to the same speed no matter how many CPUs you add, because they're just flattening out in your performance. And the reason is, of course, if you have, so this DJX2 box has 16 high performance, server grade GPUs in them. So that is a very dense compute unit. And you can imagine that at some point just data communication takes over if you can't scale out arbitrarily. And with the DJX box, because it's such a dense piece of compute machinery, you sort of stay in this one machine. And the GPUs have a very high speed interconnect that is called NVLink and NVSwitch, where the GPUs can communicate extremely fast. That's why you get this sort of super linear speed up. if you look at it in numbers from partners that they're experiencing, I'm not necessarily saying that all machine learning, if you put it on a GPU, will suddenly get 200x faster. But the ones, like we have partners that actually get those speedups already in production. So from Oak Ridge, for example, they are using XGBoost. XGBoost is a framework for gradient boosted trees, open source, and we are heavily contributing to them to make sure that it runs well on GPUs. They experience a 215x speedup. There's a global retailer, Walmart, that not only was able to increase its prediction error, but they can also run or like improve the prediction error, so reduce the error, I guess. But they can run more often and faster to do the predictions, and of course, and every little. So if they have to throw away fewer produce because they can predict better how much people will buy, the more they save, obviously. So how does a data science workflow look with RAPIDS? It's hopefully not different to a traditional CPU-based workflow. That's the whole point behind this. So in the ideal case, as a data scientist, you wouldn't even know sort of that you're using RAPIDS, with the exception that it's significantly faster, hopefully. So you have the 3 steps: data preparation, which is, you can imagine you have data sources from various, or you have data coming from various sources. You may have like your company database that has, let's take the supermarket as an example, how many bananas did they sell over what period of time and so on. And now you may have a suspicion, maybe that has to do with partially the weather, like if it's nicer out, maybe people buy more bananas because they go picnic. If it's more cold outside or rainy, maybe they buy fewer bananas. And it can have to do with maybe events, like there might be a big holiday coming up or any of those. So this other data is most likely not, like the weather is most likely not stored in your supermarket database, right? So that you would maybe use a web service to get all the weather data, to the predictions over the next 2 months, let's say. And so you have like different data sources that you then sort of have to first combine, right? You have to make sure that you match sort of the date format that your weather prediction service uses to the date format that a database uses, and maybe data is incomplete and noisy, or usually it is, so that means you have to fill in missing data, and you have to handle all those things. That's all part of the data preparation. And that is usually done, I think I have a slide about this, but I can't say now. You have sort of an abstraction, if you're using Python, an abstraction that is called a data frame. A data frame is sort of almost like it's a tabular format, so almost like a database table, you can imagine it, and you have different operations that you can use on those data frames. So that means you have one table of your product and one table of your weather, for example, and then you may want to join those 2 data tables into a new data table, so it's very databasey, as you see, and then you may want to group individual entries in there by certain categories, and then you may want to sort it and fill in the blanks, sort of, right? Those are typical data preparation pipeline. And then once you have all the data in sort of a numeric format, right, that's sort of the goal of your data preparation pipeline, is to get to usually some form of a matrix with numbers, right? All the strings in there have to be replaced with some form of a number representation so that your machine learning algorithm can work on that. Once you have that, you start whatever machine learning algorithm of your choice. Could use XGBoost or principal component analysis, k-means, k-n, dbScan, TSVD, any of those. You could of course also try a traditional neural network-based architecture if you wanted to. And then, of course, you have to sort of explore and visualize the data, because unless you're sort of in the matrix, you probably won't be able to look at the numbers and know what's going on. So you may have diagrams and presentations and the development of the error loss, for example, over time and so on. So that all those visualization features are important for you as a data scientist to then sort of estimate and judge and get a feel for where your data science algorithm may get improvement from. So if you look at the effects of all those, and that's one of the big pieces in RAPIDS, is that we not only look at sort of the model and training block, which with neural networks, that's definitely what NVIDIA focused on, but now we also look at the data preparation pipeline, and so we call that an end-to-end acceleration. So in the ideal case, data comes out of the database or the data source, let's call it, and it's immediately going onto the GPU, right, distributed, and you then stay on the GPU and do everything on the GPU, from string processing to database operation to the actual machine learning. If you look at sort of the effects that this has is, if you're on the very top, you may have the machine learning and training part, which is a significant block, but if you reduce that, let's say by 4x, 5x, whatever, this whole upper thing would get a little smaller, so that's good, of course, but you still have all the querying and you have to write to a distributed file system and so on. You have to do the ETL. So ETL is, again, the pre-processing of the data. And all those blocks would remain, right, if you don't move that onto the GPU too. And because we run distributed and stay on the GPU sort of front to end, we can get rid of a lot of those blocks and get like an overall significant speed up from that. Now, of course, I'm not sure if anybody tried to program GPUs yet. It's not hard. So if you do parallel programming in one way or another, I would even say it's often easier than a lot of our other parallelization strategies to just write CUDA right away. However, there's still, you don't want your data scientist to be a parallel programming expert, obviously. So you sort of want to make it as easy as possible. And so there are certain challenges, and especially you have to deal with sort of the data movement. Data movement is always bad because it doesn't do anything useful for you, right? You're just moving data. And especially it's then, the slowdown of a data movement operation is then always the weakest link, and especially if you go distributed in a whole data center and one node over there has to communicate with the other node over there over multiple hops, you can imagine that just crashes your speed up overall. Then another problem is that there are too many, in the data science world, too many sort of makeshift data formats that are very close to each other but just not binary compatible. And of course that means in every step you then have to transform from this ND array format to this other framework's ND array format, which is almost doing the same, but they manage the fields a little different. And so you go across and then you have to transform your data all the time. And that is, again, a performance problem because transforming data is essentially a mem copy operation with a little bit of switching a couple of things around, a little bit of metadata, and that is also useless essentially. If you don't need to do it, you would prefer not to do it. And then, of course, you wouldn't want your data scientists to actually write CUDA, right? So that means you have to have all those operations, also algorithms implemented, and then, which NVIDIA does not have as much experience as we probably should, you of course want a Python API to that, right? And GPUs traditionally, there are open source projects out there that make the GPU available in the Python world, but it's none of them is NVIDIA backed. So for the data movement, you can imagine, you have a CPU and you have some application A and B, and you sort of need to get the thing over. If you now move things onto the GPU, if you don't, and you are in a multi-node environment, or at least even if it's a single node, but you have multiple GPUs in there, if you don't make the GPUs talk to each other directly in the application, you do a straightforward porting and say, okay, this piece, I move from the CPU onto the GPU, and I just copy all the data over, and then, I copy all the data back, and then CPU does a little bit, and then I move everything over again and move everything back again. You can imagine that you're going over the PCI Express bus a lot, right? And that is not the fastest option, obviously. So what you would like to do, ideally, is that you don't, that you essentially for as long as possible keep the CPU out of the loop. The CPU is still sort of the main driver, so the CPU has the main program and has the GPUs what they're supposed to do, but you want to keep the bulk of the data on the GPU, right? So in the GPU main memory, and as I said, the GPUs can talk to each other with NVLink and NVSwitch with like super high speed, faster than, like way faster than the PCI Express bus would be. So the GPUs can still communicate with each other, sync with each other, move data back and forth, and the CPU is sort of the main driver telling the GPUs what to do, so the coordinator, but you try to avoid the actual data copies over this narrow link. The second part was too many makeshift data formats in my list, if you remember. So here's an example for that, right? And how Apache Arrow sort of is addressing that, and we are sort of, how do you say, like using Apache Arrow, piggybacking on Apache Arrow. And so on the left side you see, we have like a lot of different applications or frameworks, and they want to talk to each other, and each of them has to sort of copy data back and forth with each other, and everybody would have to understand everybody else's format, right? As I said, they're often very similar, but they're just not binary compatible, so there's some work that you need to do. And now with Apache Arrow, the idea is that Apache Arrow defines an in-memory layout of your data, a columnar layout. And for all applications that sort of adopt Apache Arrow, they can then seamlessly talk to each other because we go through this common format. You don't need to use Apache Arrow sort of as your internal while you're processing format, but at least you want it sort of at the boundaries, right, where you ingest data and where you give data out. Whenever you use Apache Arrow at this connections, then the other applications can just adapt and attach to you. And then the third one was like the data scientist shouldn't need to or shouldn't be required to write CUDA, and you wanted Python sort of accessible. So all of RAPIDS has an exposed Python API. We try to be, I have a little bit about that later I think, but we try to be compatible to well-known, not compatible, but at least inspired, if not even drop-in replacement, to famous or popular data science APIs in Python. So for the ETL part, we sort of we have a data frame approach, similar to like Spark or Pandas. And then, so data frames, if you remember, would be those tables that you can then, like on the left side, you see you have like different operators you can run on those tables, right? To select and to filter and to mutate. So any SQL-like operator that you have sort of something like that. So you're sort of writing interactive SQL in your IPython notebook. On the right side, you would see sort of how that looks in code, right? You would say some data frame with column, you pick some columns, so you select a column, and you do some little operator in there, you multiply the age by the fair, and then you show it, and then you see it in your IPython notebook. Like that's how you work with that. And if with our data frames, the data is actually on the GPUs, and you're typing your IPython notebook, and stuff happens on the GPU. So that's why I wrote GPUs at your fingertips. And for the machine learning part, we are very inspired by scikit-learn, the API. So in the ideal case, or most of the time, it's really a drop-in replacement. So instead of importing scikit-learn, you import RAPIDS, and then you should be fine. So what does RAPIDS, the sort of the software package, contain? So we decided to go open source with RAPIDS. So you can go to rapids.ai. I have a link later, and you get all the code. And so on the left side, you see sort of, it's like a whole software stack, obviously, right? You have algorithms, machine learning algorithms, and implementations of all those database operators and so on. That ultimately, of course, runs on top of CUDA one way or another, because if it runs on GPUs, it needs to run through CUDA. So the components, those three things on top, the data preparation, model training, and visualization, are the same blocks I started out with, if you remember. So that's sort of the cycle that a data scientist usually goes through. And for each of those, we have sort of software packages. Those are the green pieces that sort of implement this step. Let's start out with like those two, QML and cuGraph. Those are essentially libraries that we provide for doing machine learning. So that would be QML. Those are implementations of the different machine learning algorithms, and cuGraph provides implementation of graph analytics algorithms. So for QML and cuGraph, you have essentially, a lot of algorithms. So here's a list of algorithms in the second column that we provide. So you have decision trees, random forests, linear regression, logistic regression, k-means, k-nearest neighbor, db-scan, Kalman filtering, PCA, single value decomposition, and Bayesian. Some of them are under development at the moment, so if you keep up to date, you'll eventually get them. Some of them are out there already, one version or another. Some of them, so it's a wide field, obviously, right? Some of them, like Kalman filtering, for example, has so many variants that we, of course, focus on 1, 2, 3 important ones for now, but there are so many other variants and so on. So that is a ginormous field, but we sort of try to pick the interesting pieces. If you want to either contribute or you have a need for a specific algorithm, you can obviously always contact us and collaborate. For graph analytics, we have sort of PageRank and breadth first search and so on, which is also in the RAPIDS.ai repository. And if you just as an example for XGBoost, so we also, we try to collaborate with open source frameworks when they exist, and we try to implement it ourselves if it doesn't exist. For random forests and decision trees or gradient boosted trees, we are collaborating mostly with XGBoost, and like contributing code back to their code base to make sure that they run as efficiently as possible. And we have like a good success with that. But it's not only XGBoost, for example, we're also like working with CatBoost and are in contact with their developers, right, to help them. So it's not, we're not singling out an individual one, but we try to pick the good pieces and combine them into a software package. Again, that is sort of a very similar graph to what I showed before, so in interest of time, I don't go into too much detail. But here you see again, even if you scale up to like hundreds of CPU nodes, you're still not getting to the point where you can beat a single DGX2 in those examples that we're showing here. And so the reason is, again, because you just get overhead. When you add more CPU nodes, you're not necessarily at some point getting faster anymore. And those are a couple of benchmarks for initial algorithms, where you see the speed up in the Y direction and sort of the size of your problem in the X direction for TSVD and PCA and DBScan. So it looks very promising for a lot of those. And then again, you have the synergy effect with staying on the GPU because you do the ETL pipeline on there too. So the overall speed up then is potentially even super linear to that. I'll probably also skip that, but those are, as I said, like we're working on a lot of those actively. If you follow the RAPIDS AI repository on GitHub, GitLab or GitHub, I'm not sure, either one, you'll see sort of when the new things come in, right? And you can also obviously contribute to the bug tracker and feature tracking and so on. For cuGraph, similar. So we have a whole bunch, so that's for PageRank specifically now with over a couple of benchmarks. We are obviously always looking for real world data sets, so it's more interesting to solve real world problems than benchmarks. If we don't have anything else, we go for benchmarks, obviously. So if you have a need or good ideas of what you could do with that and try with that, then feel free to sort of get involved and talk to us. So those were the model training part. Now we look a little bit at the QDF, so the queued data frame implementation, which is sort of the API that you would use in an IPython notebook interactive session, right? So that's the thing you talk to, really. So in QDF, we adapted Apache Arrow, as I said, as the in-memory database, as the in-memory data format. And we provide a pandas-like API for QDF because there's also many data frame implementations. So Spark has one, Pandas has one, a couple of others. There's not the one standard, so that's why we take a little bit more lenient approach and say we don't have to be a drop-in replacement. We just switch Pandas to RAPIDS and it all works. But you may have to adapt a couple of syntactic things here and there. But it's essentially Pandas-like. So if you know Pandas, then you should be able to use CUDA data frames. And the important operations that we're working on are unary binary operations, of course, joins, merges, group bys, filters, and so on. So that means you can write, for example, if you have two data frames and you want to join them, or if you want to apply a lambda to a column in the database, you can write it in Pandas, or sorry, in Python, and it then will run on the GPU on your data. So we have, for QDF today, It's essentially an API that runs on CUDA, so it's written in C, C++, because that's where CUDA runs. But we have provide all the Python bindings. Potentially, if the need arises, we could also look at other languages like Julia or I don't know, Lua, whatever. But at the moment, we are focusing on CUDA, sort of with Python bindings. All the low-level pieces are written in highly optimized CUDA, C, C++, and we use the Apache arrow format to sort of import and export the data, and inside, like when the GPUs talk to each other, we use CUDA IPC, that's the inter-process communication mechanism, so that the GPUs can sort of change data, exchange data, talk to each other. Yeah. And on the Python side, the interesting line is probably the second to the last. So that means you can take NumPy arrays, for example, and just say, okay, now take this NumPy array and make it into a QDF data frame, and then all the management of the GPUs and the GPUs that are available and who gets what data and so on, that's all then be done in the background. You have, as that, like you can pass lambdas, for example, if you want to do a point-wise operation on each of the data elements, for example. You can pass lambdas, and then we're using JIT compilation through NumPy. Another big piece of the data preparation is obviously string processing. So if you imagine, as I said in the beginning, data is usually noisy, so that means, or incomplete. So if you imagine you have like a database that contains, some form of company names, let's say, right? So you sell stuff to people and you write in like what company you sold to, for example. Some of those may be very noisy, like and they are stored as strings, so you may have, BMW in all uppercase, and the next guy writes BMW all lowercase, and the next one writes BMW Inc., and the next one BMW AG, or whatever. So there are many different spellings. Somebody may even spell it out completely. And you sort of have to combine them all so that the machine learning algorithm knows that's all the same BMW you're talking about, right? So that means you need to parse strings, you need to make strings to uppercase or lowercase, you may combine them, you may do substring matches and all those things. And we are providing a library now that's called QString with NVString that can do all this. So that means it's a string processing library. Of course, there are so many things you can do with strings that we are not there yet, right? We're still building up the library. But for a lot of those operations, actually, we see very significant and promising speed up. The reason being that string processing is often very memory bound, but the GPU has very high bandwidth main memory access. So the GPU DRAM and the speed that the GPU processing units can talk to this DRAM is usually very high, higher than a CPU would have, and that's why if you can, can leverage this, you get actually also very good string processing numbers. So the last box I want to talk about on this thing, I'm not going to talk about visualization, that's usually making some graphs and things like that. But the last interesting box on here would be Dask, which is sort of the process library we use to scale out to multiple nodes. And we're collaborating very closely with the Dask developers. So Dask, I'm not sure who is familiar with MPI and does not know Dask, so because it will be a little imprecise what I'm going to say now, but if you're familiar with MPI on one of those and don't know what Dask is, then you can imagine Dask to be sort of the MPI run or MPI exit executable that sets up processes across multiple machines, right? That's sort of where the analogy ends though, so the rest is very different. But it's essentially a way to start many processes across a cluster, for example, of machines, and then make the machines sort of find each other and talk to each other. The nice thing is all the scheduler is like written in Python, and it's like very modular, so that means it fits very well in our whole ecosystem that we are working with. So it's essentially you're using you're doing sort of a MapReduce style computation when you use Dask, and so our QDF implementation sort of is designed to work well in this setting. And you can especially easily, once you go from the ETL pipeline onto the ML pipeline, when you do the machine learning, you may, like your communication library has sort of different requirements, right, that you need to do. So on the ETL side, you say, okay, I want to be failure redundant, and I want to be or resilient, and I want to sort of scale out, and I have to coordinate those guys. Once you're in ML, it's much more a traditional HPC application, where you say, okay, I need fast, reduce sum all operation. And that's all where MPI comes in, or is very helpful, or an MPI similar to MPI library, which we call NICO and CCL, which is sort of an MPI-inspired library, also open source, that has high performance GPU like collaborative GPU operations, like all reduce and things like that. And so we have sort of a bridge when you want to go out of Dask into sort of the ML style communication, which is not Dask anymore, that you hand over, or you instantiate from within Dask, instantiate sort of the communication between all the participating GPUs, and then you can switch over to sort of a NICO style or MPI style communication. So if you look into the future, for the next few months, as I said, like it's a continuous process. So if you follow the open source project, you'll see sort of what, whenever new commits come in, obviously. But our goals are, so a lot of those things are still very single GPU, not all of them, but especially in the CUDA data frame side. And we are working hard on sort of getting it not only single node, multi-GPUs or DJX boxes, essentially a single node that has in a DJX1 case 8 GPUs and a DJX2 16 GPUs. But it's still one node, right? So there's one CPU and it can talk to all the GPUs, to an actual multi-node, so cluster-based approach. And then string support, of course, is getting gradually better and better. And we have accelerated data loading in the pipeline, so parsing file formats can often, like in some of our benchmarks by now, 90% is actually reading the comma-separated value file that the benchmark comes in, and then the rest of the 10% is all the rest. So we are going to look at those file formats like parsing and Parquet, so CSV parsing, Parquet, and so on, to ingest the data faster. That we have a couple of preliminary numbers. They look very promising again. As I said, like one of the biggest effects is not only the speed up of the parsing itself, which hopefully will be very significant, but also if you have a big pipeline, and that is sort of the leftover piece. If you're familiar with Amdahl's law, that's sort of what you need to attack to get a good overall speed up. There's also a very interesting development now, which is a Python CUDA array interface. So an n-dimensional array, essentially. So we talked about before about Apache Arrow, which is a columnar layout, right? In this case, it's now dense ND arrays, where a couple of people sort of decided on a CUDA array interface and collaborating to sort of come up with essentially a specification, and the first projects are already including those. That brings it to my concluding remarks. So in the beginning, I had this, why did I become a data scientist? If you, think back, and then you actually are doing your data science, and you see that a lot of those green parts are essentially you're sitting around and possibly drinking coffee. With Rapids, hopefully, we're getting more to the point where you have more of those red pieces, which is actually work. So you can actually try out things, try your ideas, and iterate much faster because you don't have to wait as long. So that means when what you did in a day or two, sort of the development cycles, you can now do within a day. Yeah. So the interesting piece of GPUs, of course, before I conclude for real, is that we are, as you may know, good in graphics, obviously. But we also have a pretty long history by now in HPC, and now more and more with neural networks, but also with Rapids now more and more also in data analytics. And those three things is sort of my understanding, my prediction, and my hope will sort of grow together into a bigger single one, right? So now there are HPC applications that do simulation and then run data analytics on actually the simulated data, for example, for scientific discovery. And then, of course, they have to visualize it in order to tell the scientists what's going on, right? So that is sort of the new area that we're working in. And then all the individual components, GPUs, are actually very helpful and provide a lot of benefit. If you want to get involved, how to get the software, as that if you just go to rapids.ai, that will lead you to everything. Yeah, go to rapids.ai, and that should lead you to all the other places, right? And if you want to join, Apache Arrow, the GPU Open Analytics Initiative at GoAI, and then rapids.ai are the pieces you should have a look at. And yeah, get involved, get in touch, and thank you for your attention. With QNet, or what did you say? Oh, Kubeflow. Yeah, I only got it half myself, I think. I'll come a little closer. There was somebody standing up, so I only heard. So again, maybe. Okay. So.
Yeah, there is some library for RAPIDS for Kubeflow.
Okay, for Kubeflow. If we plan on integrating with that, essentially, right? Or using. Yeah. I think so too. I'm not familiar with the details. But whatever sort of makes sense and is helpful, we are very happy to work with. I think there is work going on, but I would lie if I say.
I think a simple way of deploying workloads is interesting, or
it's definitely interesting. I mean, we're working on the neural network side very much with Kubernetes now, and with also Docker containers, sort of our container thing of choice, because it, like every other container vendor is able to read Docker formats. That is sort of our deployment strategy, is Kubernetes and then Docker for things. So it's definitely will become very important once people start rolling out that more, yes. Thanks. Exactly, yeah. First you have to have the code running in it. Yep.
Just out of curiosity, how easy is it to integrate this system into a larger pipeline you have? So for example, you start with Spark and then you might need the system because of parallelization. Is it then easy also to get your results and write it to something else, or use it as an intermediate step, or how easy is it to do this?
So the question was, how easy is it to integrate Rapids in existing pipelines? Like, for example, if you have Spark, using Spark already, and you then for a certain part want to go parallel and use Rapids, and then maybe you have to write it back in a way that Spark understands it can read. So we're collaborating very closely with Spark too. So there will be announcements sooner or later to how the actual integration looks like. We definitely, our goal is that it's all seamless. So if you're the data scientist writing Python in your notebook, you should be able to switch back and forth. Essentially, maybe you have a line in here and there where you have to do some conversion, but it should be completely seamless. It's most likely, I would assume, not seamless yet. It's all still like currently we're at 0.5, I think, version. So it's not, it's not necessarily a production quality thing yet where I could say like just switch over and everything will run faster. So we're not there yet. But for the ones, like all our collaborators are very happy with the speed ups they see. So it seems to be good enough for now to be integratable in existing pipelines. But I would assume, since it's new, realistically, there's always a little bit of thing involved. Right?
Thanks. We'll have a speaker after the question. Now, let's thank the speaker again.
Thank you.